how we deal with idealizations, infinities, and pluralities, as you will see. So these, in some sense, some of these thoughts started when I was studying, and I was very puzzled by the situation that we used to solve idealized cases, as in infinite plates or perfectly round things, or in the scattering matrix, particles coming from infinity. But we could not solve precisely any of the actual cases, the real. So I found the situation frankly paradoxical, that the only cases we could solve precisely are those where we all agree do not exist. So I'd like to share with you some thoughts on this relation with the ideal, particularly concerning quantum theory, which is where I feel more at home. And the basic message is that open quantum systems should be taken as fundamental. And this is so because this is a chapter I wrote for a book published edited by Mike Cafaro and Stefan Hartmann, where another chapter of the book is their work on open quantum systems, where they precisely argue for the same thing. And so my arguments will go into reaching, in some sense, the same kind of conclusions that they did, but from a different perspective. Okay, so my name is Gemma de las Coves. As you may know, I just moved to Barcelona. But I spent 17 years in Austria and Germany, and my background is in mathematical quantum physics. So anything you ask me about the mathematics of quantum theory, I feel very comfortable with. If you ask me more conceptual questions, I will do my best, and I am here to learn from you. But I think that generally speaking, one can say I have chewed a lot of glass, using Philip's expression yesterday. Yes. All right. So I want to first argue that closed quantum systems cannot exist in the world, in the physical world. And then I want to turn to the question of whether we should conceive of the universe as in kind of the ultimate physical system as closed, and I will argue against that view. Namely, I will put forward some reasons why we should think of the universe as a plurality as opposed to a unity, something enclosed. All right. So that's what I want to end up concluding. And to that end, I want to start with a disclaimer, which is that I don't know what it means to exist. And so I read a fair amount of metaphysics or introductions to metaphysics, where they discuss questions that I feel are very relevant, such as whether time exists or what's the nature of a cause or things like that. But I never found a definition of existence. Maybe that's it's fair that this be this way, because it's such a kind of brute or kind of rock bottom concept that it can't be described. But maybe with my more mathematical mindset, I was expecting somewhere to that question be addressed. What is existence? But I never found it. So anyway, the summary is that I don't know what it means to exist. I also don't know if a physical world exists, but I will pretend I do. And I particularly will assume that there exists a physical world. And that I will refer to as the real. As you can see, that's not very carefully defined, but I'm trying to do my best here. And the ideal will be whatever is opposed to this real. So whatever, that's kind of easier. The ideal will be whatever I can tell cannot exist in the world. By the way, ideal is also a mathematical word for something completely different. The mathematical structure has nothing to do with what I'm saying here. So closed quantum systems cannot exist in the world because of 3 reasons. The first 2 are plain. The third will take us a little longer. The first is that no system can be completely isolated. That's kind of an ontological reason. It would require, for that to exist, it would require there to be no interaction whatsoever with the rest of the world. And okay, to the best of my knowledge, that cannot happen. But in fact, if it did happen, then we could know nothing about it. Because, so here I'm assuming some form of physicalism by which knowledge supervenes on some state of matter. And then knowledge is some form of a correlation between that state of matter and the state of that other system whose properties we are trying to know. And therefore, such a correlation requires an interaction. It can only kind of come to be if there is an interaction between such a toy subject and toy object. And therefore, so they would be, such a completely isolated system would also be epistemically isolated. And finally, kind of the reason that I want to kind of elaborate on has to do with infinities. So I'll try to argue that the representation, as in mathematical representation, of a closed quantum system necessarily involves an infinity, and infinity cannot be supported in the physical world. Okay, so in order for me to make this argument, I'd like to start by setting the stage and saying what is the real and the ideal in quantum theory. So the real I identify with an open quantum system, and the ideal with a closed quantum system. So from a kinematic perspective, an open quantum system is described by a mixed state, which is mathematically given by a density matrix, which is a positive semi-definite matrix of trace 1. And the ideal is represented by a pure state, which is mathematically a mixed state of rank 1, or equivalently a vector like a ray in a Hilbert space whose 2 norm is 1. Yes. With regard to the dynamics, the real corresponds to a quantum channel that is a completely positive trace-preserving map. That's the general evolution. So this is the general way to describe a transformation of a quantum state. And the ideal corresponds to unitary evolution. So there is a very far-reaching here mathematical fact, which is the fact that the description of an open quantum system can be given directly per se, or in terms of the description of a closed quantum system by means of a so-called purification. So this, in this case, this kind of bridge to the ideal is transparent. Every mixed state, for example, can be purified to a pure state. That's kind of reaching out to the ideal. And then, so from the ideal, you need to contract. You need to apply a contraction in order to get back to the actual case. Okay. Similarly, every quantum channel can be purified to a unitary evolution. In fact, these two statements are essentially the same because both of these things embody certain positivity notions, which are isomorphic, people say. This is a Choiza-Miolkowski isomorphism. And so this is kind of ultimately, the fact that they both can be both purified is ultimately like one mathematical fact. But that is the situation in quantum theory. Kind of such a pivot on the ideal is very transparent and very well controlled. We know lots of things about it, and it is mathematically, of course, extremely useful. So mathematically, the real is like a special case of the ideal, in the sense that if you like mathematically, you can only focus on that together with contractions, obviously, right? That's a misleading situation conceptually, I believe. In particular, that does not mean that closed quantum systems are ontologically first or more fundamental than open quantum systems. I think that we are continually mistaken, or we are continually misled by mathematical facts, which we overinterpret, or whose interpretation is not clear. Let me put it this way, and that would be one case. And now I want to argue that the ideal necessarily involves an infinity. Well, in physics, this is easy to do because it's quite plain. Phase transitions, for example, are only defined at the thermodynamic limit. If you want to do the actual case, you need to do finite size effects, perturbations, and that's always more or less. Zero temperature is the infinitely small. And in this case, there is a physical principle explicitly prohibiting zero temperature to exist. But as you know, in condensed matter, zero temperature is kind of the pivot on which many other statements are made. Then you will do like finite temperature effects. Similarly with ground states, again in condensed matter, ground states per se cannot exist. Or many other examples, particles coming from infinity, infinite plates, perfectly round things, plane waves, even the other eigenstates that Almut presented yesterday. Now, I believe quantum theory stands out here with respect to the rest of physics in the following sense. If the real is of finite dimensions, the ideal also has only finite dimensions. That's pretty unique. So let me say that again. In quantum theory, there's a theorem by Choi, by which if you have you don't need the theorem by Choi in finite dimensions, but if you're in infinite dimensions like C-star algebras and so on, this is also true that if you have a density matrix, say of internal dimension D, that can be purified into a pure state of dimension D squared in essence. Okay. My point here is that from D, we go to D squared. So it seems that when we move to the ideal, we do not need to invoke an infinity, as opposed to phase transitions, for example. Right? If you want to go to the ideal case in phase transition, you need to go to the thermodynamic limit. But in quantum theory, because of the purification theorem, it seems that the ideal does not involve an infinity. I cannot think of any other case in other areas of physics where this is also the case. Maybe you know of some. But I want to argue that despite this appearance, the ideal also involves an infinitive because of two reasons. One is that to infer the dimension of the Hilbert space, one needs an unbounded number of measurements of identical copies. So there are two infinities in here. First, unbounded, and second, identical. And the second reason is more conceptual, namely that the description of a complete isolation requires, so it's a statement that, so complete means that for any threshold I put with regard to its isolation, as in, look, its interaction is lower than this threshold, the statement will be a negation, like there will be no interaction that's below that threshold, right? But it's for any threshold. So it's a statement for any precision. And any theory in physics I can think of can only express such a statement as in for any precision by using the potential infinity at the very least. I will go now to the potential infinity in a second. So by using arbitrary precision. So there we have another infinity. Okay. And now I want to argue that the world cannot support infinity. So Aristotle argued that potential infinity can exist in the world, but actual infinity can't. And my translation is that potential infinity corresponds to the unbounded, whereas actual infinity corresponds to an infinite set. That is a set whose cardinality is at least Aleph 0, like the cardinality of the naturals. And but I want to argue that, so I will rely on, let's say, Aristotle's argument that the actual infinity cannot exist, but I want to argue that the potential infinity cannot exist either, cannot be supported either. And so first by addition, later by division, right? So by addition, so Aristotle said, because time is infinite by addition in the past and in the future. And well, with today's knowledge, the first seems false and the second unclear. And also the space of the universe seems to be finite. So I conclude that if in time and space the potential infinity by addition cannot be supported, then it cannot be supported in the world either. And by division, my question is, why should I believe that something can be divided arbitrarily many times? So I think that the burden of the proof is on the other side. So infinity has such extravagant properties that I find it much more sober to assume it cannot be instantiated. If you like, this is a bit of an onto epistemological argument or something like that, where if I feel very uncomfortable positing an ontology that I can never access. So I'd rather not do that. Okay, so this is my explanation why infinity cannot be supported in the world. And now I want to look at what we actually do in physics with regard to infinities. In the theories of physics, in fact. As you know, the theories of physics rely heavily on the actual infinity, on the reals, like space, time, mass, temperature. I believe that in many of these cases, the potential infinity would suffice. Maybe we will all agree that what is physically accessible is a finite multiple or fraction of a fundamental unit. Such a finite number changes gradually with time because we happen to live in a wonderful age where scientific discovery is blooming and we are continuously increasing precision, let's say. So I am fine with, so I agree that developing a theory that only works up to a certain precision would be certainly mathematically ugly, but that's not my concern, would be very contingent, let's say, to our time. So I am fine with granting a theory that allows us to describe a finite but unbounded, so multiple or fraction of fundamental units. And then I would like to see fundamental units as a brute fact of the world. Brute fact, as I learned from the philosophy books, means fact that does not need to be explained, or kind of as a yardstick provided by the world in order to measure things and then make the statement, look, that thing is 50 billion times that other thing. As we do right now, like the second are this incredible number of oscillations, it's very precise, of the decay of a cesium atom from that level to that level, and so on. So that's my argument why I believe that the potential infinity should suffice. That is to say, the rationals. And a short note on quantum theory, it relies on not only the reals, but interestingly, the reals with an imaginary part. And recently, it has been shown that this imaginary part is necessary. That doesn't go against what I'm saying. So as far as I'm concerned, that could be done with the rationals plus an imaginary part of the rationals. And paradoxically and contrary to what I am saying, we considered quantum theory on the hyperreals with an imaginary part. The hyperreals are an extension of the reals. So every hyperreal is an infinite sequence of reals. So the reals are a subset of the hyperreals, and they behave very well. They form a field, ordered, complete, blah, blah, blah. And we could solve some long-standing questions in quantum theory over the hyperreals with an imaginary part, such as that there is NPT-bound entanglement, if you've heard of this kind of classic question in quantum information. And my question is then, why do we do quantum theory over the reals with imaginary part as opposed to the hyperreals with imaginary part? You see, I don't have a criterion why. So first, I think we shouldn't use the actual infinity. But second, if we do use the actual infinity, why do we use one as opposed to another? The only rudimentary criterion would be that the reals seem somewhat simpler. In fact, they have the same cardinality as the hyperreals. But this criterion is not very solid, I believe, because the reals are full of monsters, right? Like essentially every real, its only description is itself, full of paradoxical properties, and so on. So I mean, all the craziness goes in the reals already. Interestingly, computer science does not rely on the actual infinity, but on the potential infinity. If any of you has ever tried to prove that a physical problem is of a certain complexity, the first thing you have to do is discretize the problem. That's usually painful and ugly. Particularly if you take the most standard model of computation, a Turing machine, everything is finite except for the tape, which is unbounded. Right? So there's a finite alphabet, finitely many transition rules also on a finite alphabet. It's all well controlled, except for the table. So in fact, I see Turing machines as a principled way to reach out to infinity from the finite, or to the potential infinity. This view, by the way, is more explicit if you look at the dual description of a language accepted by a Turing machine, which is provided by the grammar that generates that language. A grammar is a generative set. It's a finite set of rules that can be applied an unbounded number of times in order to generate any string in the language. But I contend that this is also physically not very meaningful, precisely because the notion of unbounded has no scale. Particularly if you, so as you know, a problem is called decidable if there is a machine that eventually halts and accepts or rejects the string. This eventually is extremely non-physical, because everything in physics has a scale. Eventually can mean a ridiculous number, completely ridiculous. I don't know, a goggle, 10 to the 100, or a goggle times the age of the universe. That's a finite number, and from the perspective of mathematics, the same as the number 3. And of course, that brings me to really ask, what is the importance of proving computational complexity results in physics? And I worked a lot on that over the past years, and I'm not clear on that. People will say that's why classes like P and NP are introduced to talk about polynomial as opposed to non-deterministic polynomial. I have issues with all of these definitions that ultimately have to do with this not careful regard of the potential infinity. I like to illustrate that with a quote, which kind of parallels the opening sentence of Anna Karenina, by which, as you may know, that any finite language, I'm talking about formal languages here, right? Any finite language is trivial. Trivial means regular, if you know a little bit about regular. It's like the most trivial there is. But infinite languages are non-trivial in their own ways. So you can't talk about the complexity of infinite languages. You can say, is it context-free? Is it context-sensitive? Is it recursively enumerable? Is it co-recursively enumerable? Is it in NP? Is it in P? Is it in XP? Is it in MIP star? Right? But that only makes sense if the language is infinite. If it is finite, there's nothing you can say. So yes, like in the opening sentence, say happy families are all alike. Every unhappy family is unhappy in its own way. I'm not fine with that situation. And just a comment, another way how I think computer science ideas can inspire physics ideas is in the reach from the finite to the infinite from the finite. And in that respect, we have recently seen local physical interactions as the grammar of physics. And we have classified these physical interactions as grammars and kind of characterized their complexity from that light. Particularly for the Ising model and whether they are, well, they are all context sensitive. So I think some ideas are beautiful and valuable. Others need to be taken with some care. Okay, so obviously, what's kind of at the background of everything I'm saying is the fact that we use infinity, particularly, both infinities, in fact, because of their beautiful mathematical properties, right? So, for example, the potential infinity. It is good and it is well-grounded to distinguish between finite and unbounded. And then the actual infinite. It's so wonderful that all limits exist. And it's a field, and there are all these beautiful properties, but we shouldn't be embezzled by the mathematical beauty and kind of readily conclude that, I mean, it's certainly useful, but that doesn't mean it's real or it's faithful to any kind of actual physical thing we're trying to describe. So I believe that what we actually need is a mathematically well-grounded notion of infinite for all practical purposes. So we're using infinite for all practical purposes. But I think that is not justified. That's kind of what's going on here. And if we had that, that would be wonderful, because we could formalize things like emergence. By the way, everything that I said may be wrong, because there's a like very important new result in computer science, but it's coming from some people doing quantum computation. It's caused many big waves, called this MIP star equals RE result. So it's a result within computer science about quantum computational complexity classes, but that has solved a very old conjecture within C-star algebras called the cone embedding conjecture. Anyway, so they provide, so they have so-called non-local games, where two players need to do some things. Anyway, so they provide a so-called game where if the two players are of infinite dimensions, then that game can be won with probability 1. But if the two players are of finite dimensions, for any finite, then that game can be won with probability at most 1/2. So there's a gap. So if there was any way of realizing that game in the world, and we would witness winning probability over 1/2, we could conclude that each of those systems is of infinite dimensions. This would be absolutely wonderful. This would be a way of witnessing infinity in the world. I don't know if that can be done. So I don't know if there are principled obstacles why this can never be realized. At the moment, the paper is very complicated. It's like 200 pages, lots of technical results on top of other very technical results and so on. So it's very obscure for me, and I cannot enter there. But I think this is a wonderful possibility. Okay. So with that, I'd like to move to arguing that the universe itself should be conceived, if anything, as a plurality. So the first is a message of humility. I think I have nothing else to say here. But I also want to give you a logical reason. And that has to do with the paradox of trying to reach out beyond a last edge. Okay, this is so imagine you go to the very end of the universe, there's an edge, and you stretch out an arm. So this is a paradox proposed by Archetypus, not sure how to pronounce it, as usual, the Greeks, wonderful thinkers. That is, of course, nonsensical, because if it's the last edge, how are you supposed to stretch out an arm, right? But I want to share with you that this paradox has many reincarnations and many far-reaching consequences. Saying that something is unbreachable or inconceivable or unthinkable or ineffable is in fact contradictory. By the way, all of this is taken in my own words, so mistakes are mine, by this wonderful book by Graham Priest, which is one of my favorite books and I really love it. So, for example, take Parmenides. What is not cannot be or be thought of. Well, we're thinking of it right now. Nothing can be known. That's what the skeptics would tell us. Well, then that very statement cannot be known either. Everything is relative. Well, then so should this very statement be. Something is indescribable, like Kant with the nomen. You may disagree, okay, with Priest, but that's kind of his approach to the problem. Well, if it is indescribable, or if you can pass no judgment on it, you're contradicting yourself, because that very statement is a quality, is assigning a quality to the thing, indescribable, or you are passing that very judgment on that thing. Or something cannot be predicated. Hey, you just predicated it. So he explains how such this structure, let's say, this logical structure can be found at the limits of cognition, conception, expression, and iteration. And the skeleton is something called enclosure schema, I believe, by which you posit that something is contained, say, within a set or a collection, that's closure. But this something transcends this set, usually by construction. That's called transcendence. And this something exists. That's called existence. Well, that's a contradiction, because something cannot be in and out of a set at the same time and exist. So endeavors based on logic, such as mathematics, computer science, theoretical physics, they essentially always deny existence. That's how they get out of this contradiction. And this has devastating consequences. I will show you some in a second. For example, it implies that there are infinitely many types of infinity by Cantor's theorem or by Gödel's theorem. The consequences are unbelievable. I'll show you some in a second, okay? So this is very far-reaching. It cannot be fixed. I believe philosophy, when confronted with this contradiction, is not so clear about what should be done. For example, the statement I showed you in the previous slide, probably many of you will disagree with Priest's conclusion. We say we shouldn't discard Kant and such, it's like so hastily. Interestingly, I'm unclear on what the physical world does with that. I mean, we very often say that the physical world cannot support contradiction, but I'm not so sure about that. And I'd like to illustrate that with the grandfather's paradox that I will mention in a second. If you have an opinion, I'd love to hear it. And also, interestingly, art is not bothered by this limitation. So I believe that they kind of face this limitation, this contradiction, without any fear. And they just go ahead and do lots of self-reference and negation. And I am fascinated by that. But trying to understand how that works begs the question of what is art? And that's a complicated. And so in the logical world, the mechanism for transcendence is self-reference and negation, or diagonalization by Cantor. So that's, in essence, the liar paradox. If I say I'm lying, you will conclude I'm lying if and only if I'm not lying. So you cannot decide whether my statement is true or false. So my statement transcends the set of statements that are true or false. If you try to fix the problem by adding a third value of truth, I will be able to construct a new paradox of self-reference and negation that will transcend this one, and so on forever. You cannot fix it. This sentence is false. We were talking about semantics the other day. It has the same structure. Gödel's first incompleteness theorem provides a statement that says, I am unprovable. Well, it's provable if and only if it's not provable, so you conclude that it is undecidable. And again, it cannot be fixed. So as soon as a system reaches the level of expressivity by which it can express self-reference and negation, you fall in this trap, or you are bound to these limitations, and that never ends. The halting problem is uncomputable. That's typically shown by assuming that it were computable, then you would feed it its own description, negate the result, then that machine would halt if and only if it would not halt. Contradiction, so we deny the premise that there was a machine that computed it. Russell's paradox, set theory, of course, the set of all sets that do not contain themselves. It contains itself if and only if it does not contain itself. So that implies that naive set theory doesn't work. Cantor's theorem, I'll show you more in a second, which implies that there are different types of infinity, and particularly infinitely many types of infinity. The grandfather's paradox, if you go back in time and kill your own self, that's like self-reference and negation in time. But that has to do also with, here I wonder what is first, causality or the avoidance of paradoxes? I'm not sure about that. And all of these are made precise in a theorem that's very unknown called Lovier's theorem, written in a very obscure paper, the language of category theory in '69, made available by Janowski in a beautiful paper 2003, which is, however, not as precise. We also slightly generalized it recently. The bottom line is that you can clearly lay out the conditions under which you will be able to construct such a paradox. So this mechanism for transcendence limits what can be formalized, computed, learned, known, and some philosophers would say even said to exist, like the anti-realists, or said to be true. You can attack the correspondence theory of truth like that. So it's very far-reaching. Okay? But I want you to see it as a mechanism for transcendence. Okay? Whenever someone claims, here is an ultimate closure, you can attack it by self-reference and negation. And I just want to show you kind of a simple case where we understand very well what's going on. And what I've been saying so far is the statement that no system can consistently describe all of its own attributes. So for a system, take a set, and for attribute, take a function, f, from the set 2, 0, 1. Okay, it's a binary attribute. Okay, and identify that function with its extension. That is to say, with a set of elements in S that are mapped to 1, right? Okay, such that f of n is 1. Okay, such an extension is not an element of the set. It is a subset of S. Therefore, it is an element of the power set of S. Right? The power set is the set of all subsets. Okay, so I'm identifying an attribute with an element of the power set. For example, if S had 3 elements, then as you know, the power set has always 2 to the cardinality of S elements, in this case 8. So like the empty set, the sets with just 1 element, with 2 elements, and with 3 elements, right? And I would identify the attribute not being B with this one. That's not being B, right? Okay, but now Cantor's theorem, which works by self-reference and negation, the diagonalization method, is the statement that a set can never be put in one-to-one correspondence with its power set. Never. 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 So no matter how super mega infinite and super mega complex that is, these will be more so. Never, 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 never. So if you take here the naturals, these will be of a higher cardinality. If you take here, and then you can go on, like the power set will be of a higher cardinality, and the power set of the power set will be of a higher cardinality, and so on, right? So this implies that there are infinitely many types of infinity. I mean, we have to imagine some absolutely crazy things. So self-reference and negation can never be captured from within the system. So why should there be an ultimate closure? I mean, why should I? Okay, and I just want to end by saying that we humans are very special. So I can engage in self-reflection. That doesn't mean I can achieve self-transparency. Or that doesn't mean I can describe all of my own attributes. But there's something fairly unique, it seems, in the mind. And maybe I would here agree with George's comment yesterday that we seem to transcend and enclose ourselves. That's my take of that. That is also the content of this proto-theory of consciousness put forward by Hofstadter in Goyal et Scharbach. In fact, I have recently argued that we carry this wound of infinity, the fact that we are part and whole at the same time, and somehow the syntax of our being. I try to say things along this direction because I think that the human nature is really special. Okay, so with that, I'd like to end with some final remarks. The first is that biology cannot resort to an ideal as we do in physics. That's interesting. In biology, everything is a mess, and there is no home where they're like, okay, I can describe this case exactly. So we shouldn't have the illusion that such a pivot on the ideal is generalized. I wonder what a quantum theory based on open quantum systems would like. As far as I see, the biggest difference to our current theory has to do with the dynamics, because I didn't say that, but if you take quantum channels as fundamental as opposed to unitary matrices, such quantum channels are generally indivisible as quantum channels. So that's suggesting that the time evolution would be discrete. And what would physics without the actual infinity look like? There are some recent papers by Del Santo and Gizan where they consider this question, in other words, and they conclude that, deterministic theories, kind of cutting out all of these infinite decimals of the reals, become non-deterministic. So they say that the real numbers are like the hidden variables of classical mechanics. Mathematics without infinity, I guess constructivism could bring us there. And generally, a question that's kind of lurking in the background is how can we, perishable open systems, even conceive of the ideal? Yes. And with that, I'd like to end it here.
Thanks so much. We have about 10 minutes for discussion. I always hate to reduce time this way, but that was my
We'll never start if we keep being kind to each other.
I have a question about the idea you said that we need a well-grounded notion of infinity for all practical purposes. Well, I feel that there is a kind of tension between the idea of for all practical purposes and well-grounded. Namely, maybe in this sense, recursion can be thought as a way to tackle infinity for all practical purposes, and recursion is quite well grounded. So.
Thank you, but I don't think so, because recursion is to me the same as reaching out to the unbounded, right? So recursion, approved by induction, right? That's a statement for all n. I want some sort of, I said mathematically well-grounded, so kind of with some beautiful mathematical properties and so on, of saying if I reach, for all n smaller than 13.7 billion, that is the case. For larger than 13.7 billion, we enter into a new regime, and so on. You see what I mean? So recursion doesn't help me. Recursion is what we have already. It's the same as a Turing machine. Okay, maybe we can discuss this more later.
Yeah, but this is the meaning of for all practical purposes.
No.
We are fine.
No, we're not fine, I think. No.
May I go on? Oh, it seems that you're attacking the idea of approximation. The birth of modern science is based on idealization. There's a wonderful quotation from Daniele where he talks about the necessity of overcoming the impediments of matter in order to imagine that there is an light plane without friction. And now I'm asking you, are there inertial systems in the world, but what could you do without the first law of motion? Newton is well aware that it is possible that no inertial systems exist because maybe the gravitational law affects everything that is endowed with mass. And the other problem is maybe you should think about how can we apply mathematics to the physical world if there is such a chasm between ideal models and the world. And finally, I think there's a lot of complex, biology is full of mathematical models if you look at what they do in Santa Fe.
Yes, Santa Fe, precisely, yes.
Geoffrey West, for instance.
Yes.
So I have other questions, but I think I've already put too much on the table.
Thank you. So, clearly, this way of proceeding that I am criticizing has been extremely successful. So that for sure. It has brought us very far, right?
It will be successful. By induction.
No, induction doesn't work. Induction cannot be justified. So no.
Well, but it's still quite good
No.
for all practical
No.
purposes.
No.
Sorry.
So I think that answering your question requires having a clear position on the relation between the formal and the world, or between mathematics and physics. And unfortunately, I don't have such a position. I don't know how they relate. So that's the best I can do right now. Maybe we can discuss this more later.
I've been very lucky because coming here, I had the venture sitting next to her So we had a great conversation and I learned so much from Gemma.
Thank you.
Thank you. I really like your talk, but I was wondering about one thing. You listed a number of semantic and logical paradoxes there.
Yeah.
And I was a bit astonished that you didn't mention anything. Perhaps you disagree, or if you disagree, but anyhow, Solomon Pfefferman has written a lot about that, these things in light of logic and predicativity. And as far as I remember now, his general idea is that we should dismiss impredicative concepts because of our cognitive problems. And
Who?
do you have any view about that?
Excuse me, I didn't get the name of who did.
Solomon Pfefferman.
I don't know that. Sorry. I could have also mentioned Tarski's undefinability of truth. By the way.
Yeah. Yes.
Okay, I should look that up.
Yeah.
Thanks.
Pfefferman discussed all these cases.
Okay, thank you.
So in mathematics, to me, infinity appears in two ways literally on the page. First in terms of the infinity symbol, and then in terms of division by zero, and which is any proof that goes through division by zero is you can conclude anything, but the infinity symbol is an expression of infinity and defined as such. Could it be that that definition can be questioned, that we already have a mathematics without infinity because a division by zero is inconceivable or can't exist?
Sorry, I didn't quite get the question.
Yeah,
What
so
was it?
you're asking if we should define a mathematics without infinity.
Yeah, I think that's constructivism. I think some of them, I know too little about that, but some people have, I guess, have similar concerns. Yeah, so I think they've come some, but a symbol, maybe we shouldn't mistake the symbol for, it's fine that there is the symbol, but so what's your point with the symbol? I don't understand.
I mean that my question is, could it be that mathematics already is without infinity?
Well, some part of mathematics, constructivism, I guess, is, but most of it, infinity has very beautiful properties mathematically, and they do not bother about, or some do bother, right? Constructivists, but generally they do not need to bother as physicists do about whether the walls they are constructing bear any resemblance to something else.
Right, we have one final question.
Yeah, thanks for the wonderful talk. I have two brief clarificatory questions. So one is, you talk about the universe as a plurality. I was wondering what you mean with plurality, or whether you could say a bit more about that. And the second question is, so I'm intrigued by your distinction between the real and the ideal. And I was wondering to what extent the real corresponds to the physical world, or how you think about that.
Thank you. So the first question, I didn't make that very explicit, but whenever you conceive of something as a unity that amounts to positing a closure, because to think of, this is wonderfully explained by Priest, how just to be within a set is essentially the same thing. And so the lesson that there is no ultimate closure is the fact that some collections cannot be conceived as a unity. For example, the set of all infinities. Cantor went mad with that, trying to think of the largest infinity. That's contradictory. There's no such thing, and you have to think of that set of all infinities as a plurality in the sense that a unity has more conditions than a plurality. You expect some things to be well-behaved of a unity that you do not expect from a plurality. So in that sense, I meant it. And the second question is very good, and it's kind of at the very core of the beginning of these arguments. And unfortunately, I cannot answer very precisely or very well. All I can say is what I said at the very beginning about some things I see cannot exist, but what exists, that's the best I can do. I think partly relates also to tomorrow's question.
All right, thank you very much.